screencast for homework for AP Physics 2 for this year. What we end up have happening here are the problems that deal with thin film interference, diffraction. So these are all constructive and destructive things for the most part. So the first problem is a little bit easy. It's problem 1. It's saying how long does light take to travel through 3 millimeter thick piece of window glass. So you do have to look up into the chapter for the index refraction of glass. That's 1.5. So I believe on your formula sheet, and I'm going to take a look right now because I've got it somewhere, is the idea, yeah, that n is equal to c over v. So v is equal to c over n. So that's 2 times 10 to the 8th meters per second. So now if you know the speed and you know the distance, that's pretty easy to find the time. Again, just make sure you don't have a death by algebra 1. For problem 4, it says light has a wavelength of 670 nanometers in air. If it's in a transparent solid and 420 nanometers, what's the speed of light in the solid? So the first thing you got to do is you can take those two wavelengths and get your index of refraction, so that's 1.595. Again, your index of refraction is going to be a minimum of 1. That's in a vacuum, and air is slightly more than 1, but it rounds to 1 for many purposes. And so then you can, this 1.595 makes sense. So to get the speed there, again, I'm going to rearrange this, use this equation, 1.88 times 10 to the 8th meters per second. For part B of this, it's saying what's the light frequency in the solid. So frequency is constant. So if we know our general wave formula, which is on our formula sheet also, then what we can say is frequency is velocity over wavelength. You could either choose that in a vacuum or you could choose it in the solid itself. Either way, make sure that you use the correct numbers because those answers should be the same. Because frequency doesn't change depending on the material you're in. For problem number 11, it says a double slit experiment performed with a light of wavelength 600 nanometers. Bright interference fringes are spaced 1.8 millimeters apart, where the fringe spacing be if the light is 400 nanometers. So in this case, you could use a couple different versions of this. This is going to probably be a small angle approximation. So essentially, if I look at this, if the wavelength is down to about 2/3 of what it would initially be, 400 instead of 600 nanometers, then the sine theta also has to decrease to 2/3. So for small angles, sine theta and tan theta are very similar. So if we have this as being 1.8 millimeters, then that would go to 1.2. So that kind of uses a version of the formula here. I don't think the AP would ask a question quite like this. They would probably ask how would they change. They may not ask a numerical value. For problem number 17, you're given something that says, oops, flipped the wrong page. 1 centimeter wide diffraction grating has 1,000 slits. It's illuminated by 550 nanometer wave, where the angles of the first 2 diffraction orders. So the first thing is we're going to use our general equation here. In order to get this, first of all, we've got to find D. Well, we've got 1,000 slits per centimeter, 100,000 slits per meter. That's N. D is equal to 1 over N. So that's 1 times 10 to the negative 5th meters. So we could end up doing this, getting our angle. So for our first order wavelength, we would have 3.15 degrees. Second order, close to double that, 6.32 degrees. P25 is a thin film interference. Question, I think I'm not sure if we went over this one in class or not, but basically we have thin oil film that floats on water. So I've drawn that here. Air is going to be 1.00, oil 1.25, water 1.33 for the indices of refraction. And it's saying, what's the thinnest film to produce a strong reflection for the green light of wavelength 500 nanometers? They really should have said 500 nanometers in air. So we're going to need to find the wavelength in oil by dividing that by the index of refraction. So that's 400 nanometers in oil. So when we look at this, the light ray reflecting off the top surface of the oil and off of the surface of the water would both flip and have a phase shift because the light's reflecting off of a more optically dense substance. So therefore, that would be constructive interference if we had 0 path length difference. So the thickness of the film, which is distance down or up, we could think about the fact that twice the thickness, because this light down here goes down and back up, would have to equal 1 full wavelength. So the idea is the thickness would be half a wavelength thick to have constructive interference. So that would be 2 times 10 to the negative 7th meters, or 200 nanometers. Another thin film interference problem for number 27. So again, what I've got here is, it says solar cells. There's a silicon solar cell that's coated on the outside with a layer of silicon dioxide. So this coating is above the solar cell. Index refraction 3.5, index refraction 1.45. So kind of similar to the last one we did. Both these will flip or have a phase shift when reflecting off the surface. And at this particular case, you actually want minimum thickness to minimize reflection. So that's destructive interference. So essentially, twice the thickness, because remember, this light going down and coming back up has to travel an extra distance of twice the thickness. It should equal half of a wavelength. And so in that case, twice the thickness is equal to half a wavelength, so our thickness should be a quarter of a wavelength. Again, I've got to take a look here and see, hey, if this was 700 nanometers in air, in the coating, that would be 483 nanometers, so a quarter of that is 121 nanometers thick. Again, I'm not sure if the AP would be that specific numerically. They may ask for it in terms of a wavelength. But if they do ask for a numerical value, remember, wavelength gets shorter as you go into something that's more optically dense. Problem 48 we went over in class, so we had a 2.5 meter distance here. We had bright fringes that seemed to be about 0.6 centimeters off, so that's 0.006 meters. So I could get this angle here. That angle, when I look at d sine theta equals m lambda, and that 0.006 meters was between bright fringes, so that's a 1 wavelength difference in path length, so I put 1 here for the order number. So essentially, I'm rearrange this equation to solve for d. 2.2 times 10 to the negative 4th meters. Problem 57 is the last one. We went over this in class also, so this took kind of a whole page for me. We had 500 slits per millimeter. That's 500,000 per meter. So that's distance between them of 2 times 10 to the negative 6 meters. And so the key with this is it was asking you what the wavelength is, but what you really had to do is multiply these things through because we were given the angles. And notice that there was a relationship between these two values, these two d sine thetas. And if I look at that, in my mind, this is basically 1 1/3 times what that is. When I did the math, that ended up being that. So this is a 4 and this is a 3 ratio. So I then plug in m is equal to 3 for the 45.7 degree angle, 4 for 72.6 degrees, and then I work back either of those values plugged with their equivalent angle would get you the wavelength. So that's how I got 477 nanometers. So it's really just multiplying out the left side of our d sine theta equals m lambda equation and noticing what I get and noticing how these two numbers relate to each other. So hopefully that makes sense, and hopefully you understand this chapter because we spent a moderate amount of time on it, but I also know it's fairly confusing.